Okay, so let's add a few more points to this geothermal story. The WRI, World Resources Institute, has put out this nice report on next generation geothermal considerations and opportunities for responsible development. So, what are the points? They are basically looking at some of the points that we already looked at, the types of geothermals, where they are headed, what are the technical challenges and other barriers, what are the policy options. So I'm not going to read policy options, etc. This is much more focused on the US, so I'm not going to bother with that part. But it's a nice report to add to what we already looked at. This looks like California here, as we already saw in the last podcast on geothermals. California is one of the major geothermal producers. What are the highlights? So we'll read the highlights, the executive summary, and few more nice figures from the rest of the text. Geothermal energy provides clean electricity 24/7 and could play an important role in achieving a 100% clean grid that is cost effective and reliable. As we said, it can provide a base energy flow, unlike solar and wind, which have intermittency issues. Next generation geothermal technologies, which are in various stages of development, hold potential for widespread deployment across the United States and globally if cost reduction trends continue. We'll look at some trends, and essentially we have already said that just using directly what exists has limited geographic extent, but if we start using enhanced and advanced geothermal systems, then we can probably push it into every region. Whereas conventional geothermal facilities drill to reach natural natural underground hot water reservoirs to generate energy. Next generation geothermal technologies drill into hot rocks without sufficient naturally occurring fluid or permeability. So then you need injection well and a production well, as we saw before. Some of these next generation geothermal technologies use advanced drilling techniques borrowed from the oil and gas industry, but with key differences that lower the environmental risk profile. So the point also is that oil and gas companies, which are already petrified about being pushed out of business because of climate change and move to renewables, can actually get into this business without much further upskilling of their workforce and so on. To commercialize next generation geothermal, it will be necessary to further develop new technologies and techniques, proactively address potential environmental risks, and overcome key barriers such as high upfront financing needs and lengthy permitting processes. So there is detailed sections on these barriers and new technologies and techniques, which I'm going to skip. It's a little US centric, but obviously they are applicable elsewhere as well, since everywhere we have lengthy permitting processes supposed to be for protecting people, obviously, and water and air pollution, etc. also have to be avoided. What is the executive summary on top of these the highlights? Geothermal technologies provide electricity around the clock and could play an important role in achieving 100% clean electricity. So US has some goals by 2035, but we can see that just like oil and gas and coal, geothermal can also provide dispatchable clean energy and important grid services, and is not subject to the same weather-related constraints as wind and solar energy, and holds promise for storing energy for long durations. Dispatchability is basically where you crank up production when the demand goes up during a hot day, midday, or during harsh winter storms, and so on and so forth. Usually the fossil fuel power stations use something called peaker plants, which use fossil fuels or sometimes dirty fuels like coal. So you have to be careful. Either way, we want to phase out fossil fuel anyway. Next generation geothermal technologies could be deployed at greater scales and over much wider geographic areas than conventional geothermal technologies, which use just the upper part of the surface where it's closely available, and we already said those are geographically limited. But there are many reports that you can look up. We mentioned IRENA before, the International Renewable Energy Agency under the the UN. Department of Energy in the US looks at this a lot, and there are estimates made about next generation geothermal cost that could cost effectively yield from 90 gigawatts to over 300 gigawatts of capacity in the US by 2050. This is a substantial part of the 700 to 900 gigawatt of clean firm power needed to decarbonize the electricity sector. So you want to decarbonize, get to net zero by 2050, so you want to have as many clean energy sources as possible. It could even be higher if technological breakthroughs succeed in accessing and harnessing heat at the greatest depths and temperatures. Theoretically, the Earth produces enough heat to single-handedly meet all global electricity demand. We already said that in the previous podcast. Multiple types of next generation geothermal systems are in various stages of development. Enhanced geothermal systems that we looked at are currently the most advanced, with projects already delivering electricity to the grid. So we'll look at this briefly again. Costs have been falling significantly, as we will see. Closed loop geothermal systems have commercial pilots. The EVER cycle that we talked about in the previous podcast, that is not fully operational at utility scale yet, and super hot geothermal applications are the most nascent, where you get supercritical temperature and pressure water. Just to handle them, we need newer materials probably. So they would use either conventional, enhanced or closed loop systems at even greater temperatures, the super hot geothermal applications. Compared to other sources of clean electricity generation, next generation geothermal technologies have relatively fewer emissions, land use impacts, water use and critical mineral reliance, which is all good news, especially compared to even solar and wind. We'll look at some comparison tables as well. Although any drilling includes the risk of environmental impacts such as induced seismicity and groundwater contamination, these risks are lower for the next generation geothermal compared to oil and gas. Okay, so that should be good news as well. Some next generation technologies and applications do pose some risk of induced seismicity. This can be managed through the use of protocols that assess risks and adapt operations as needed. That's where policies, implementations, regulations, etc. will be very necessary. With proper management, the risk of induced seismicity is lower for the next generation geothermal than other subsurface technology applications. So they include, fluid in other subsurface energy industries, fluid imbalances and pressure differentials are the primary causes of induced seismicity. For example, in unconventional oil and gas production, re-injection of wastewater for underground disposal is the primary cause of induced seismicity, not the hydraulic fracturing itself. So hydraulic fracturing is where you pump water to fracture the rocks where shale and other fossil fuels are hidden. You pump them out, and then the wastewater that produced is injected back, which actually is done in a way that actually seems to induce seismicity, mostly micro earthquakes, I think, as they are called. But obviously we are only one big accident away from scaring everybody about fracking. Groundwater contamination risks are lower for next generation geothermal energy than oil or gas. Okay, that's compared to fracking and so on. So all good news. Proper casing and cementing procedures to protect groundwater aquifers, and to date no geothermal projects have caused groundwater contamination, but geothermal also has been a small fraction of the overall energy production, especially compared to oil and gas, right? Geothermal has received less policy support than other clean energy technologies, and several key barriers must be overcome to scale the industry, such as high upfront costs, financing challenges, and long site development and permitting processes. So I won't read this further. This has got some more text in the main section. To accelerate next generation geothermal in a responsible manner, federal and state policymakers should consider these key policy options. So we'll read this much. Proactively address environmental risks and concerns, streamline permitting, invest in research, development and demonstration to reduce costs of existing techniques, develop and validate new techniques and materials, and support mapping of underground heat sources. Obviously that will help commercialization. De-risk early stage development and exploratory drilling through financial support that can reduce upfront costs. Drive demand for clean, firm power and increase the cost competitiveness of next generation geothermal. So government can do a lot in that direction as a part of the climate action and decarbonization. Of course, increase public awareness through public communication and community engagement. Okay, so there is an overview of next generation geothermal technologies, and this is what we can do. We already looked at these. In fact, characteristics of geothermal technologies. Conventional geothermal is basically hydrothermal, where hot water reservoir is there. You just tap into it and you can pump in. So developers here actually access naturally occurring hot water reservoirs, usually near tectonic plate boundaries or volcanic areas. Fluids circulate openly in the system, limited additional resource potential, so only few places have this, so it's geographically very limited, as we saw mostly on the western US side, for example. Enhanced geothermal systems we discussed before, where you are doing more active pumping and extracting. So developers access hot rock and create fissures via hydraulic fracturing. They add water and or other fluid that circulates openly through the fissures as it heats up. High resource potential, multiple operating demonstrations delivering electricity to the grid already. So again, here is where you have to worry about contamination, seismicity and those things. Closed loop geothermal system, where it's not, you are recycling. So developers access hot rock through well bores in a closed circuit system and mine the heat from the rock through conductive heat transfer. So as hot water comes in, you use some conduction processes to extract heat from the pipe that is carrying water at very high temperatures. High resource potential, again, first demonstrations underway, higher costs and lower heat flow rates than enhanced geothermal systems. So geothermal systems in super hot conditions occur using any of the above techniques. Developers access very hot rock, typically at great depth, which produces supercritical fluid that has properties of both a liquid and a gas, so it behaves in a funny way and will need new materials. And this is virtually unlimited resource potential in early experimental stages, and we don't know what risks it may carry as well, but we talked about the potential for it, because higher the temperature, easier it is to produce electricity, which is the main goal, instead of just directly using it for heating water or drying cement, fishing, farming, other things we talked about. What are the grid attributes and operating characteristics of the next generation geothermal? Again, I'm only reading very briefly. Next generation geothermal technologies hold potential to provide power around the clock and to provide reliability services that will be increasingly needed as the power sector approaches 100% clean electricity. Geothermal can serve as a source of clean, firm power, which is widely understood to mean a carbon-free source that is available when needed. Other sources of clean, firm generation could include nuclear, hydropower, hydrogen turbines, or fossil fuels, and biomass with carbon capture and storage. Okay, read that again. Geothermal can serve as a source of clean, firm power, which is widely understood to mean a carbon-free source that is available when needed. Other sources of clean, firm generation could include nuclear, hydropower, hydrogen turbines, or fossil fuels and biomass. So you use fossil fuels and bioenergy, but you make sure nothing leaks out. All of these technologies produce power that is controllable. Most also have some ability to increase or decrease output as demand changes, so they are deployed when demand goes up or down. Reliability services provided by clean, firm power and other energy technologies. They are comparing various things: next generation geothermal, natural gas combustion turbine, natural gas with carbon capture and sequestration, coal with carbon capture, hydropower, nuclear, solar, solar plus battery storage, wind, and wind plus battery storage. You have voltage control in all these items. Inertial response is there except solar. Primary frequency response, so you can see does not exhibit attribute here, and this is partially exhibits attribute in terms of inertial response. This is about frequency control, and there are other regulation, load following, spinning reserve, and so on. So details that I will not go into, but you can read in the report which is available, and it's a very nice report. Black start capability, and this is on-site fuel inventory etc. Sorry. Okay, so let's look at some figures from the main text that will add some oomph to support for geothermal. Basically, the report is very optimistic about geothermal, so everything they provide supports their claim that next generation geothermal is a savior in terms of adding to energy portfolio for decarbonization and net zero. Cost of electricity for next generation geothermal, cost of enhanced geothermal systems. So this is the levelized cost of electricity in US dollars per megawatt hour. 2024 deep binary. You remember we looked at binary where hot water is not directly used or flashed. You take the hot water out and then you boil something else, water or some other fluid with a lower boiling temperature. This is deep flash where you are using the water that's available, but you end up releasing some contaminants as we talked about. 2024 near field binary, so near where the reservoir of heat is available and not on the reservoir itself. So this is binary. And flash, so flash has lower cost, but it has higher potential for contamination, right? So this is the 2030 DOE target in terms of levelized cost of electricity, so lower than anything that exists now. And 2035 they want to drop it even further. So anything you do eventually will come down to relatively what else is available. You want clean energy, but you also want to reduce costs, and that's the best way to drive out coal and natural gas and oil. And coal is already facing this issue of being driven out by just economic considerations and not necessarily environmental considerations. Cost of electricity for geothermal, next generation geothermal, continued from the previous figure, is closed loop geothermal system that we talked about. So in 2023 it was at 300. You can compare, this is almost 50% or less of that cost, and DOE wants to accomplish much lower, so around 60 or 70 dollars per megawatt hour in terms of levelized cost of electricity production. Cost improvements over time in enhanced geothermal systems. This is cost and drilling time across wells in Fervo's Project Red and Project Cape Station. So these are costs per foot in dollars per foot. So you have well 1, well 2, well 3, and so on. So cost per foot, and drilling days spud to total depth. So you can see costs have basically fallen. This is drilling days here, and this is the cost. So with the newer and newer wells, the costs have dropped for drilling and cost for foot. Okay, and finally here another figure, cost improvement in enhanced geothermal systems. Average drilling times at DOE's Forge demonstration site, that is the Frontier Observatory for Research in Geothermal Energy's Forge. Average drilling cost in foot per hour. The deeper you drill, the more you have to worry about the drilling cost per foot, right? So Forge well in 2017, early 2021, late 2021, Forge well in 2022, and standard oil and gas. So it's gone up, but we are still much lower than oil and gas rates, and we are not likely to contaminate or induce seismicity as much as oil and gas can, especially when they do fracking. Okay, so environmental impacts and considerations, always a critical aspect. Most of the existing literature on geothermal environmental impacts focuses on conventional geothermal resources with some discussions of EGS. Understanding how next generation geothermal operations and risk pathways differ from conventional geothermal and other drilling intensive industries such as unconventional oil and gas development or fracking is a key to proper management, and there are other details that I'm not going to read it. Just a few more words. Although all drilling includes the risk of environmental impacts such as induced seismicity and groundwater contamination, procedures for next generation geothermal reduce that risk compared to oil and gas development. For other environmental impacts including land use, water use, emissions, wastes, and critical mineral use, geothermal performs as well as or better than other clean electricity technologies on a life cycle basis. So just look at some numbers here. Blue water consumption over the life cycle of geothermal compared to other types of energy. So green energy is what's falling, and blue energy, there is blue water is what's the surface water. Blue water is surface water and groundwater. Okay, so biomass is in this range in terms of water consumption, liters per megawatt hour in a log scale. So hydropower is large, oil is here, and geothermal is a larger range but towards the lower end, and its mean and median are over here. So this is concentrated solar power, coal, nuclear, oil, solar PV and wind. Okay, so solar PV and wind are lower, but we are obviously facing intermittency issues here, whereas geothermal will not have this issue. Greenhouse gas emissions estimates for selected electricity generation and storage technologies. Fossil fuels very high in terms of median life cycle greenhouse gas emissions in grams of CO2 equivalent per kilowatt hour. So that's coal, oil and natural gas. Electricity storage for hydrogen fuel cell, lithium battery and pumped hydro is low here. Other electricities, biomass, solar, hydropower, nuclear, wind also in the same range. Compared to geothermal electricity, conventional geothermal with flash, enhanced geothermal with binary reduces it, and conventional geothermal with binary reduces it here as well. Okay, just keep in mind that you want to reduce costs and use less water and emit as little as possible. Land use impact of different electricity sources. Biomass gets a lot of flack because it could impact water use, food security issues, food prices could go up and so on. Wind with spacing, solar PV, ground mounted, natural space gas with spacing. So here we are looking at hectares, photovoltaics, terawatt hour. Spacing includes land in between physical components such as space between wind turbines or drilling wells. So you have to consider that as part of the energy production system for land use requirements. Biomass from residue is biomass from the byproducts of agricultural processes, and dedicated biomass refers to new crops grown for combustion. And nonetheless, compared to all these biomass, wind with spacing, solar PV ground mounted, natural gas drilling with spacing, coal, hydroelectric single purpose dams just producing energy and doing nothing else, natural gas footprint, biomass from residue or new, so wind footprint, conventional geothermal stands here. Nuclear is lower, but you know that nuclear leaves a lot of space for safety around it. Here is the hypothetical timeline for next generation geothermal project on federal lands. Time is going down this way into the future. So developer, federal government, state government, finance and utility, looking at project location activities, leasing, permitting, environmental analysis. At the state level, it's the same thing: leasing, permitting, environmental analysis, and interconnections and power purchase parity, PPA. Power purchase agreement, okay. So these are just broad, 2 to 4 months, 6 to 12 months, so estimates. I won't read all the details, but you get the idea that these things take time. So you are going into 1 to 1.5 years for developers and for states and federal and states, and then you have for utility scale deployment, you have 4 years on average when you worry about interconnection and so on and so forth. Okay, I'm being brief about it because it's very much based on one country, and you will need to worry about how this can be applied to other places around the world, because we are talking about maybe using these ideas everywhere, because drilling down is possible everywhere if you go to enhanced geothermal systems. So it should be possible everywhere with similar costs in the end. But right now, let's say rich country like US is ahead in these things because DOE has put a lot of money into research and various other analysis that is needed. In the last podcast, for example, we saw a map of the US with temperatures at 10-kilometer depth. We need to do this for anywhere we want to drill, because we'll be drilling into hot rocks and not just near surface reservoir of hot water. Okay, so enhanced geothermal systems is what can allow you to expand it into many regions, and that requires drilling into hot rocks. Okay, so let me leave this here for now. It's a nice addition to what we looked at in the previous podcast with just a few more details. Okay.